Okay, I think we should start. It is almost 10 o'clock, 10 to. Uh, so let me clarify at the beginning itself that since Professor Nangaonkar had an issue for dealing with the finite volume methodology for steady state heat conduction problem, I am going to deal with the session. Myself, Professor Sevakkar, I am working as in the Mechanical Engineering Department of College of Engineering and Research, Hausari, Taluka Ambegad, District Pune. Uh, I welcome all the participants to this session, fourth session in the faculty development program on computational fluid dynamics for beginners, uh, organized under or sponsored by AICT under Atal Academy. Uh, we will be starting with our fourth session in the FDP. So I welcome all of you. Uh, so I'll be begin with the content of the program, content of the. So what we are going to do, in fact, today is that we will be dealing with pure diffusion problems in CFD-HT. I am using this synonym CFD-HT because CFD is usually associated with heat transfer as well. So many times this word CFD-HT is also used for computational fluid dynamics. So what we are going to do, we have been introduced to the overall theme of computational fluid dynamics by Professor Atul Sharma, and he has explained us what are the various stages in the computational fluid dynamics, like pre-processing, the solver stage, and post-processing. So we'll be picking up a simple problem to begin with. He has also introduced you to the entire Navier-Stokes equation. So this entire Navier-Stokes equation essentially consists of three phenomena, like we capture the convection in the fluid, we capture diffusion in the fluid, uh, which is heat conduction if there is a heat transfer, and there are some body forces, there are some pressure forces, and so on and so forth. So the entire Navier-Stokes equation comprises of all these components. What happens if we try to go ahead with the solution methodology for entire Navier-Stokes equation in one go? It becomes very difficult for us to understand the solution methodology. So what we do, we break the entire Navier-Stokes equation into small pieces by considering particular phenomena. For example, we are going to consider, to begin with, the conduction phenomena in heat transfer, or diffusion phenomenon, diffusion of a momentum, only diffusion of the momentum. Then we will consider pure convection independently. Then we will consider conduction and diffusion together. And once we do this, we will consider the entire Navier-Stokes equation. So today's session, both the sessions, session at 10 o'clock and 12 o'clock, both these sessions will be dealt with pure conduction or pure diffusion in the computational fluid dynamics and heat transfer problems. So what I am going to do, I am going to take you through again I am going to revise in very brief, in a very short, whatever has been covered so far by Professor Atul Sharma and Professor Nangaonkar yesterday. So essentially, there are several approaches to the fluid dynamics. Let me clarify at the beginning itself that in fluid mechanics or heat transfer, the most important goal is to obtain the velocity distribution, pressure distribution, or temperature distribution if the fluid flow involves heat transfer. Once you obtain the distribution of a velocity, pressure, or the distribution of the distribution or the distribution of temperature, we can obtain the parameters which are of engineering importance. The parameters like drag coefficient, parameter like lift coefficient, Nusselt number, skin friction coefficient, all these parameters are of engineering importance to us. And to determine these parameters, we need to know the velocity distribution, the pressure distribution, and temperature distribution within a flow domain. If we know all these parameters, then if we know velocity, pressure, and temperature, we can determine any of the engineering parameters which are of importance. So, how to determine velocity, pressure, and temperature? There are several methods. I mean, traditionally, there were few analytical methods used by the people. There was a complex problem, complex number theory, which was used by many people. Many people carry out non-dimensionalization, or maybe you can do the dimensional analysis of the phenomena and try to obtain the velocity or pressure distribution in the given domain. However, all these methods have got certain restrictions. Even there are some experimental methods. I mean, we can make use, we may use experimental methods to carry out the experimental methods to obtain the solution for the velocity and pressure. However, all these methods have got certain limitations, and then the alternative approach, or at least a complementary method, came with the birth of computers. And that method is, of course, a computational fluid dynamics. The performance to cost ratio of computers increase at a spectacular rate, and it doesn't show a sign of slowing down even today. I mean, today you can possibly, some of you must be watching this particular program on your mobile itself, so you can understand the performance to cost ratio of using computers. So with further increases in both computing speed and memory of the affordable computers is of course certain in the coming future. The memory is going to be available with you at affordable cost. So solutions of all those equations which yesterday Professor Nangaoker talked about, solutions of the equations of fluid mechanics on computers has become so important that it occupies the attention of perhaps third of the researchers in fluid mechanics. Almost, I mean, 1/3 of the researchers in fluid mechanics are nowadays using computational fluid dynamics as a technique for obtaining solution to velocity, pressure, and temperature. And this field is known as a computational fluid dynamics. I mean, this is a different kind of understanding which I have tried to give to you. So what is CFD? CFD is nothing but flows and related phenomena can be described by partial differential equations, which you have studied yesterday. To obtain numerical solution, one has to discretize these equations. What is discretization? Discretization is nothing but conversion of all the differential equations into that of algebraic equation. So what we do, we essentially do algebraic. When we say we are doing discretization, it means we convert either integral form of equation or the differential form of equation into an algebraic equations, which is an approximate form. And then solving these discretized form of equations using numerical methods is computational fluid dynamics. As in case of experiments, the accuracy depends on the tools of measurement. In case of a CFD, the accuracy depends on the quality of discretization. And for carrying out the discretization, there are several methods available in the literature. Like for example, finite difference method is there, finite element method is there, and finite volume method is there. Yesterday, the difference between finite difference, finite volume, and the advantages and disadvantages of finite volume and finite difference method were discussed by finite volume method were discussed by Professor Atul Sharma. So I don't want to go into those details because my objective is to take you through the finite volume methodology. We have seen yesterday that finite volume methodology works better for the complex problem. And the accuracy of a computational fluid dynamics depends on the quality of discretization. The quality of discretization, as discussed yesterday, is better if we make use of a computation finite volume method. Before I go ahead with the actual finite volume method, I need to tell you that there are several components of the numerical solution method, or I will say there are several components of computational fluid dynamics. What are those components? The computational fluid dynamics. Yesterday, Professor Sharma told that it's pre-processing, solver, and post-processing. But then, if we go into more depth, we can understand. We understand that there are several components, or we can describe entire computational fluid dynamics with the help of these components. Like it consists of certain mathematical models. All the governing equations which we make use of are our mathematical models. Then there is certain discretization method, which may be finite volume method, finite difference method, or finite element method. It consists of a coordinate and a basis vector system. I mean, you can have either Cartesian coordinate system, spherical coordinate system, or maybe the cylindrical coordinate system, depending on the nature of your domain. Then the most important part of computational fluid dynamics, component of computational fluid dynamics, is a numerical grid. In fact, grid generation itself is one of the courses which are which are many times offered by the teachers. Grid generation is a very important part, which essentially governs the quality of the solution which you obtain. Then there are certain approximations which we need to introduce when we go ahead with the solution methodology, which we will learn as we go ahead with finite volume methodology. These approximations, how do you introduce these approximation, is also an important component. Then of course, once you convert all the partial differential equations, or for that matter the integral form of equation, into algebraic equation, then how to solve those algebraic equation is a part of a solution methodology, which many times is called a solver step in the CFD. And then once you decide the solution methodology, you need to actually implement the convergence criteria also. So convergence criteria is a part and parcel of your part and parcel of components of CFD. So among these, what we are going to do, we are going to pick up a simple problem, and we are going to make use of all these components. We will be going through each and every step as I have, which is mentioned here, to understand a simple problem. To begin with, we will deal with a very simple problem. Then the complexity of level of the problem will be increased slowly as we proceed. Yesterday we have gone through the governing equations in CFD. I am reiterating those equations. Like for example, the first equation, divergence of rho u vector is equal to 0, is a continuity equation, which is nothing but a mathematical representation of a principle of conservation of mass. Then second is the momentum equation, del by del t of rho u vector plus divergence of rho u vector is equal to minus grad of p plus mu grad square u vector plus x vector. This is my momentum equation, in which the first term represents the unsteadiness in the flow. The second term represents the convection in the flow. On the other side, we have a pressure force, then viscous force, and a body force. If you look at this equation carefully, the left hand side of the equation represents rate of change of momentum. So rate of change of momentum is nothing but force. Now in this equation, if you take rho onto other side, the left hand side then represents, if you take rho onto other side of the equation, then left hand side represents the acceleration. For example, del u by del t, this is acceleration, rate of change of velocity with respect to time, then which is a temporal acceleration. Similarly, this is, if you take rho onto other side, what is left is del u by del x plus v del u by del y. So this is also an acceleration. However, all of you must have studied in your fluid mechanics course at second year undergraduate level. This is a convective acceleration, or it is a spatial acceleration. So according to Newton's law of motion, Newton's second law of motion, the acceleration is equal to force per unit mass. So the moment we take rho onto other side, this becomes my pressure force per unit mass. This becomes my viscous force per unit mass. This becomes body force per unit mass. So this is my momentum equation. Then I have an energy equation which was introduced by Professor Sharma and Professor Namgaonkar as well. It's del by del T of rho T plus divergence of rho u vector T is equal to K by Cp grad square T plus Q bar, wherein Q bar is the heat generation rate. This is my heat conduction. This term represents the heat conduction. This is the convection of a heat, and this is unsteadiness in the system. So this is unsteadiness, convection. So if you compare momentum equation and energy equation, you will find that the form of equation is almost similar, the same form. So we can represent both these equations with the help of a single parameter. Maybe we can call it as phi. These equations can be normalized also or non-dimensionalized also. It is good practice to obtain the solution in the normalized fashion, because then you obtain the solution in a generalized fashion. If your solution is generalized, it is possible for the other researchers to compare their research with that of yours, or you can also compare your results with that of the results reported by the other researchers. So if we go ahead with the normalization, like for example, if I want to have normalize my x coordinate, I normalize it normally using some characteristic length, and then x upon characteristic length gives me the non-dimensional x coordinate. Similarly, this is non-dimensional y coordinate. Time normally I normalize by using characteristic length upon characteristic velocity. Velocity is normalized by using velocity upon characteristic velocity, and so on and so forth. Pressure is normalized by normal dimensional pressure upon rho u infinity square. Similarly, theta is also normalized like this. If I make use of all these normalization factors and put those in this equation, what I obtain is non-dimensional governing equations. So non-dimensional governing equations are like this: divergence of u vector, that is the capital U. This capital U is a normalized velocity now, is equal to 0. And similarly, if I do the non-dimensionalization of the momentum equation, I find that the momentum equation is governed by Reynolds number. So it's a Reynolds number which essentially governs the flow. That's what I'm trying to communicate to you through this particular equation. Similarly, if I normalize or non-dimensionalize the energy equation, what I obtain is a non-dimensional energy equation. And if you look at this non-dimensional equation, it is usually governed by Reynolds number into Prandtl number. So Reynolds number and Prandtl number, these are the numbers which govern energy equation. Energy flow, or for that matter, heat transfer, is governed by Reynolds number and Prandtl number. I hope you are able to listen me, and you are able to. I'm clearly audible.
Yes, sir.
Okay. Let me very quickly check. If there is some,
Yes, sir, you are audible.
yeah,
You are
and the
audible.
PPT is also visible, right?
Yes, it is visible, visible.
Just wanted to confirm it in between. Thank you very much for your confirmation. Okay, so now what I'm doing, I am representing those equations in a Cartesian coordinate form. I mean, earlier the equations which I showed you are in the coordinate free form using vector notations, but I am now representing those equations in a Cartesian coordinate form for the understanding purpose. So my continuity equation now goes like this: del u by del x plus del v by del y is equal to 0. Momentum x momentum equation is del by del t of rho u plus del by del x of rho u plus del by del y of rho vu upon del y. On the other side, I have minus del p by del x, which represent pressure force, plus u del 2u by del x square plus del 2u by del y square. Plus maybe I have the body force also, which I have not shown here, but you can write it plus capital X, plus X, that is my body force. So here is the y momentum equation. Instead of u, I have v, which is shown in the yellow color now. In this equation, this v is essentially what is important to understand here is that in this equation, momentum equation, there are two velocities. So one velocity is actually a convected velocity and another is a convecting velocity. One is a convected variable, another is a convecting variable. So u is something which is forcing, one velocity is forcing the other velocity to move. So that's the concept of the convection. And in y momentum equation, it is v which is a convecting velocity. So sorry, v which is a convected variable. V is a convected variable. So the momentum is being convected. The y momentum is being convected, and y momentum is generated by v velocity. So this is my y momentum equation. In the same fashion, I can write down the energy equation also: del by del t of del by del t plus or del by del x of rho ut plus del by del y of rho vt. On to other side, I have k by Cp del 2t by del x square plus del 2t by del y square plus q bar. Now look at this equation carefully. This is my conduction. This is heat generation. This is convection, and this is unsteadiness in the system. So if you compare now the x momentum equation, y momentum equation, and energy equation, we can write down those equations, three equations, in a single with the help of a single variable, let's say phi. Phi is u velocity for x momentum equation, v velocity for y momentum equation, and temperature for energy equation. If I am considering 2D equations, if it's a 3D equation, then maybe we can have third component of velocity, and we can write down z momentum equation as well. So in this equation, the first term represents unsteadiness. This the other two terms on to left hand side of the equation represent convection. This is diffusion. Diffusion is the heat conduction if it is a heat transfer equation, energy equation. Otherwise, it is a diffusion of momentum. And this is a source. Source can be either heat generation or maybe the pressure term can be absorbed into source term. So source can be these pressure terms which I'm talking about here. This is pressure term, this is pressure term. These can be absorbed into the, the source term. And thus we can write down a generalized equation. The purpose of writing this generalized equation is that if we are able to solve this generalized equation, we can simply replace the variable either u, v, and t, and we can solve x momentum, y momentum, or energy equation. So that's something about the governing equations, which I thought I should reiterate so that you are connected with what has happened so far. You get connected with the things. So now what I am going to do, I am going to take you through a simple problem, simple heat conduction problem. And maybe I will also take you, if time permits, through a simple fluid flow problem also wherein only diffusion is present. In fact, if it is a fluid flow problem, only diffusion is not possible. It is a hypothetical problem, but try to understand. Our objective is to understand the finite volume methodology. Our objective here is not to go through the details of fluid mechanics or heat transfer as such. We are going to solve the problems in fluid mechanics and heat transfer, but our objective is to understand the finite volume methodology of computational fluid dynamics. So if all of you must have studied, if it is a fluid flow, if it is an incompressible and inviscid fluid flow, we can represent it in terms of grad square psi is equal to 0, where this psi is nothing but a stream function. This similarly, if I have a problem wherein only heat conduction is occurring, then only heat conduction there is, and that too a steady state heat conduction. Then from this energy equation, what we can do away with this term, because my heat transfer is unsteady, steady state. Then there is no convection. Let us assume there is a heat transfer in a solid material. So there is no motion of the fluid particles, so no convection, nothing. So I can do away with this term. And if there is no heat generation, for example, I can do away with Q bar. That what I am left with, I am only left with del 2t by del x square plus del 2t by del y square is equal to 0, because k and cp cannot be 0. So del 2t by del x square plus del 2t by del y square is equal to 0. So that becomes an equation for steady state heat conduction equation. That's what I'm showing here. Steady state heat conduction equation. Del 2t by del x square plus del 2t by del y square is equal to 0. Right? So our objective is, to begin with, our objective is to solve this equation for T. As I said, once you obtain the temperature distribution, we can obtain any other parameter of engineering importance. If my heat transfer process is unsteady, then, but with only conduction, then this term will not be there. So this 0 and Q bar is also 0. Then what I am left with, del T by del T is equal to K by rho Cp. Sorry, I am this rho here. There has to be rho. So K by rho Cp del 2T by del x square plus del 2T by del y square, which I can write like this. Cp del by del T rho T is equal to K by K grad square T. Or maybe I can take rho and Cp onto this side by assuming rho to be constant. We can take it out of the differential. Then K by rho Cp is nothing but my thermal diffusivity. I can use that term here, and of course Q bar is there. So these are my equations for pure heat conduction problem, and our objective is to solve these equations. How to solve these equations using finite volume methodology. That is what we are will be trying to understand in the present session. So what we are going to do, we will be considering a simple problem wherein there is a square plate, two-dimensional square plate, and that square plate is subjected to various types of boundary conditions. Like, let's say the temperature is constant on the boundary. Let's say the bottom wall is insulated. Let's say the right wall is subjected to certain boundary conditions, like QW is constant, that is, some heat is constantly supplied. And let's say the top wall is subjected to boundary conditions such that whatever heat is conducted is being convected. Whatever heat is conducted is being convected. I mean, these are the possible boundary conditions. We can obtain the solution for the boundary conditions such that this boundary is maintained at 100 degrees, this is maintained at 200, this is maintained at 300, and this is maintained at 400. So essentially, what I want to communicate is that there is a square plate which itself forms a computational domain. There is a square plate, and this square plate is subjected to several boundary conditions, and I want to, if it is subjected to several boundary conditions, then I want to obtain the temperature distribution within this plate. The plate is of dimension L1 and L2. I want to obtain the temperature distribution within the plate. That is the objective. Once I obtain the temperature distribution within the plate, I can find out some of the engineering parameters like heat transfer across the edges of the plate can be determined. But I mean, although I'm saying I want to determine temperature distribution, but my objective is to understand the finite volume methodology. So the most important and the first step in obtaining solution to such kind of a problem is the discrete representation of the domain and grid generation. Grid generation doesn't mean only only dividing the entire domain into small control volumes. We need to obtain certain geometrical parameters as well. So this L1 into L2 is my domain now. What I do when I want to do the discrete representation of the domain, I draw some vertical lines, I draw some horizontal lines. In this particular problem, I have drawn the vertical and horizontal lines which are equispace for the sake of simplicity and for the sake of understanding the finite volume methodology. So, yeah, is there any question by the way, because somebody has put on his. I hope I'm going well. So this is my domain in which I have drawn some vertical lines, some horizontal lines. The moment I draw the vertical lines and horizontal lines, my domain is divided into a small control volumes. These small control volumes are called cells. Now these cells are represented in terms of their cell centers. So the yellow circles which I have drawn here are nothing but the cell centers, which are drawn at the center of the corresponding control volumes. A representative cell center is shown here by P. Then capital E is a east neighboring cell center, capital W is a west neighboring cell center, capital N is a north neighboring cell center, and capital S is a south neighboring cell center. At the same time, I have drawn some blue dots on the boundaries. On the boundary, what do I do? I assume that there lie certain cells with volume is equal to 0, but there are some cells and its cell centers are represented by these blue dots. So all these blue dots are the cell centers. However, the cells which are formed around these blue cell centers have volume is equal to 0. However, the volume of cells which are represented by yellow cell centers is nothing but the product of, let's say, delta x and delta y. So delta x, delta y represent the volume of cells which are represented by yellow cell centers. Now, having identified these cell centers are required to be nomenclated. So to nomenclate these cell centers, what we do, we use a running indices like I and J. So I and J, these are nothing but the running indices with the help of which I can nomenclate these centers. So for example, my I goes from 1, 2, 3, 4, 5, 6, 7. 7 here, I max is equal to 7. in this particular case. Similarly, my y goes from here 1, 2, 3, 4, 5, 6, 7. So 7, Jmax is also equal to 7. So this is just a nomenclature. The yellow cell centers here, we call normally it as interior control volume cell centers. And interior control volume cell centers, for interior control volume cell centers, the running indices goes like this. I is equal to 2 to Imax minus 1 and J is equal to 2 to Jmax minus 1. So within this, we have the interior cell centers. For example, my left boundary is represented by I is equal to 1 and J is equal to 2 to J max minus 1. I is equal to 1 and J is equal to 2 to J max minus 1. So this is my left boundary. Right boundary is represented as I is equal to I max and J is equal to 2 to J max minus 1. All these points. Top boundary similarly is represented as I is equal to 2 to I max minus 1 and J is equal to J max. The bottom boundary is represented as I is equal to 2 to J I max minus 1 and J is equal to 1. So this is my boundary. So this is a discrete representation of the domain and the nomenclature of the cell centers using running indices I and J. So this is only representation, physical representation or diagrammatic representation I have shown to you. However, when we do the grid generation, we need to determine certain geometrical parameters of this domain. What are the geometrical parameters which are required to be determined? I need to know the when I will be solving the actual finite volume equation or the algebraic equation later on, which we are going to do, I need some geometrical information, and that geometrical information is required to be derived as a part of grid generation. So in a grid generation, what we do, we try to we find out the x and y coordinates of all the cell centers. Then we also try to find out the area of each of the faces of the cell. There are 4 faces: east, west, north, south. We also try to find out the area. Size of these faces, delta x and delta y, is required to be determined. Then we also need to determine the volume of the faces, volume of the cells. Sorry, volume of all the cells is required. Cells are required to be determined. And I also need to determine the distance between neighboring cell centers and cell center under consideration. Let's say P is a cell center under consideration. This is each neighboring cell center. So the distance between these two, I need to determine. Distance between P and W is to be determined. P and N is to be determined. P and S is to be determined. So all this is to be determined. Is how to determine that is shown here. How do we determine? This is a representative cell I am showing here. This is my east neighboring cell, this is west neighboring cell, north neighboring cell, and south neighboring cell. This is small e represents the east face, small w represents the west face, small n represents north face, and small s represents the south face of the cell under consideration. Now, how do I find out x coordinate of a cell under cell center under consideration? For example, let's say x p. I can calculate it by, I know where I have drawn vertical and horizontal lines. So I know the x coordinate of these vertices, all the 4 vertices. So this is my northeast vertex, this is north W, northwest vertex, this is west south vertex, this is east south vertex. I know the x coordinates of all these vertices. I add all these x coordinates and divide it by 4. What I obtain is the x coordinate of point P. Similarly, I know the y coordinates of all these 4 points. I add those y coordinates, divide it by 4. What I obtain is the y coordinate of point P. Similarly, I can also determine the size of the faces. Size of faces is either delta x or delta y. Delta x I can determine by using, let's say, any of the vertex here, and the difference between this and this, x coordinate of this vertex and x coordinate of this vertex. That is xse minus xsw. That gives me delta x. Similarly, delta y is, it is, maybe you can use y nw and y sw. So this gives me delta y. As I said, I also need to determine the distance between neighboring cell centers. So for example, let's say this distance between capital E and capital P is delta xc. So this delta xc can be determined because I know xe I know, xp I know. This I have determined here. By using these expressions, I can determine the x coordinates of all the cell centers. So once I know the x coordinates of all the cell centers, I can take the difference between two and I can find out the distances between neighboring cell centers. Like delta xc is x capital E minus x capital P. Similarly, delta xw is x capital P minus x capital W. This is there. Delta ys is, sorry, delta yn is y capital N minus y capital P. Y capital N minus y capital P. Similarly, delta ys is y capital P minus y capital S. So once I determine the distances between neighboring cell centers and the cell center under consideration, I need to also determine the area of the faces. Each cell has got 4 faces: east, west, north, and south. Let me clarify one thing. The area is always treated as a vector quantity. So direction is an important parameter for the area. The area through which the fluid comes in, if I consider that area as a positive, then the area through which the fluid goes out can be considered as a negative area. Or the area, let's say my heat is flowing in x positive direction, then if I consider this area as a positive, this will be negative. If I consider this as a positive, this will be negative. The area through which heat goes out, we will be considering that area as a positive area, and the area through which heat comes in will be considered as negative. So if I represent a delta SE as the area of east face, then delta SW negative will be the area of west face, and that will be equal to delta Y. There is a typographical mistake here. Please correct this. This is delta Y. Similarly, delta Sn is area of north face is also equal to area of south face, but it's negative, and that is all equal to delta X. This is again, I mean, these two are required to be exchanged with each other. There is a typographical mistake. I'm sorry for that. And then we also need to determine the volume of each and every cell. So volume of a cell is given to you by delta Vp equal to delta X into delta Y. I hope I am able to communicate what is done as a part of grid generation. So in a grid generation, what we do, we try to determine, we represent the entire, we in a grid generation, we represent the entire domain into small sizes of cell, some finite number of cells. Those cells are represented in terms of cell centers, and those cells are represented in terms of cell centers, and those cell centers are nomenclated using running indices I and J, and the geometrical parameters like x and y coordinates of the cell centers are determined. The sizes of the cells are determined. The areas of the faces of the cells are determined. Distances between neighboring cell centers and cell center under consideration is also determined, and volume of all the cells is also determined. I hope I am able to communicate what is grid generation. I hope I'm audible and my my presentation is clearly visible to all of you. There is a question by Yogesh Ahire. Can you please can please you repeat this slide again? Which slide you are saying, Professor Ahire? You can turn on your current slide. You mean to say this one?
Geometrical.
Okay. See what we are doing here. We are trying to determine the geometrical parameters like x coordinates of all the cell centers. Here I am giving expression for cell center under consideration, that is xp. We take the addition of x coordinates of all the vertices like this and divide it by 4 to obtain xp. Similarly, we take the addition of all the y coordinates of all the vertices, add those, divide it by 4 to obtain yp. I hope you are able to get this, how to determine x and y coordinates, Professor Yogesh.
Yes, sir. Yes, sir. Yes.
Okay, then what we do, we calculate the sizes of the faces, delta x and delta y. These are the sizes of the faces. Because I know x and y coordinates of the vertices, I can use that information to determine the sizes of the faces like this. XSE, x minus XSW. This is XSE, XSW. That gives me delta x. Similarly, for delta y, I can use y NW, that is this y coordinate minus this y coordinate. I obtain delta y. I can also calculate delta XW, that is distance between cell center under consideration and neighboring cell center, best neighboring cell center. So XP minus X capital W, that gives me delta XW. Similarly, delta XC, delta YS, and delta YN. Delta SC, delta SW, these are the area. As I said, area is a vector quantity. The area through which heat goes out or fluid goes out, if I consider that as positive, the area through which it comes in is considered as negative. So delta SC minus delta SW, the delta SC is equal to minus delta SW. That is all equal to delta Y. As I said, there is a typographical mistake. Similarly, I can determine north and south areas. And the area volume of a cell center under consideration is delta X into delta Y. Because this is a two-dimensional problem, it is delta X into delta Y. Else there will be delta Z also. Is that okay, Sir Yogesh?
Yeah. Yes,
huh?
sir. Yes, sir.
Okay. So let me proceed.
Sir, can you make your slide full screen, sir?
I will do that now. I just for the sake of looking at the chat, I did that. I will make it full screen. Is that clear now? Is that okay?
Yes, sir. Yes, sir. Thank you.
So let's proceed. So this was a discretization of a domain. Now what we will do, we will consider the equation and we will discretize the equation also. What is discretization of the equation? Discretization of the equation is to convert either the partial differential equation or the whole integral form of equation into that of algebraic equation. Here we are going to make use of a finite volume methodology to do that. So my governing equation, which we have seen at the beginning, is grad square t is equal to 0. Instead of t, now I am using variable as phi, because later on we can generalize it. So grad square phi, the form remains same, so doesn't make any difference. So this grad square phi, if I apply to small control volume, let's say any of these control volume, if I apply that grad square phi is equal to 0 to small control volume, in an integral form, I can write it as integral over delta v grad square phi into dv. dv is an operator, and grad square phi, I mean, this is all equal to 0. This is what we have learned. So this is my governing equation in the integral form. Now this integral is written in terms of a volumetric integral. Now, this volumetric integral can be converted into a surface integral using Gauss divergence theorem. All of us have studied Gauss divergence theorem during our undergraduate mathematics. When we convert volumetric integral into a surface integral, the first thing happens is this volumetric operator changes to surface operator. Volumetric integral is converted into a surface integral, and in doing so, one of the grad goes away from the equation, and what is left is grad phi. And grad phi dot n cap. N cap is nothing but the unit vector in the normal direction. This has to be introduced to consider this gradient in the normal direction. So what is done? Volumetric integral has been converted into surface integral. Now, this delta S which I am showing here is the entire area of surface area of the face, surface area of the cell, and the surface area of the cell consists of east, west, north, and south faces, south areas. So there are 4 areas. So what we can do, we can disintegrate this integral, like integral over delta SE grad phi for east face into DSE plus integral over delta SW grad phi W into DSW plus this for north face plus for south face. So I can divide this integral into 4 terms, one for east face, another for north, south west face, third for north, and fourth for south face, east west north south face, and I can sum those 4 terms together. So summation over the faces east west north south of integral over delta SF. Now delta F will be either east, west, north, or south. Del phi by del n. Del phi del n represents the normal gradient. This gradient has to be taken in a normal direction. Into DSF. Again, DSF is either DSE, DSW, DSN, or DS south. So what is done? Volumetric integral is converted into surface integral. Surface integral is divided into 4 different areas and then summed up together to obtain this equation. So this is the exact representation of the integral equation form of equation. Now what we will do? We will introduce an approximation. See, this del phi by del n is not known to us, but we can obtain the value of del phi by del n by considering, let's say I know the value of temperature here, value of temperature here. Somehow, maybe through initial guess or some initial condition or whatever, I know those values. So if I know those values, what I can do? I can take the difference between this temperature and divide it by the distance between 2. If I do that, I will be able to obtain the temperature gradient. D phi capital E minus phi capital T divided by delta XE. I will be able to obtain the temperature gradient, but that temperature gradient will be available at the point of intersection between the lines joining capital E and capital P and the area. So here somewhere, what I do, I assume that this temperature gradient prevails over the entire surface. This temperature gradient prevails over the entire surface. And I assume that for a particular instant, it is constant. And then by assuming it to be constant, I take this gradient out of integral sign. And what is now left inside the integral sign is DSF. And integral of DSF is delta SF. Because I know that area, it is delta SF. So my approximate representation now goes like this. Summation over east west, approximate representation of grad square phi, integral over delta V of grad square phi dV. The approximate representation goes like this: summation over east, west, north, south faces of del phi by del n at f into delta sf. This f is either east, west, north, south, or delta s faces, and delta sf is either delta se, delta sw, delta sn, or delta ss. So it can further be approximated as, I can now approximate this del phi by del n can be replaced in terms of phi e minus phi p divided by delta x. See here, phi e minus phi p divided by distance between two. For west face, it can be written as phi capital P minus phi capital W divided by distance between two, that is delta xw, multiplied by this area, that is delta sw. This term. Next, for north face, it is phi capital N minus phi capital P divided by distance between two, that is delta yn, multiplied by this area, that is delta Sn. And this is the next term. Similarly, the last term is phi capital P minus phi capital S divided by distance between two, that is delta ys, and multiplied by the area. So that is phi p minus phi s divided by delta ys into delta s. So this is now my approximate representation of integral over delta v of grad square phi dv. This is approximate. If this is all equal to 0, if I set, then that becomes the algebraic equation for steady state heat conduction. Look at this equation. This is algebraic equation now. It is discretized. It's no more integral or differential equation. All the terms are algebraic in nature. So this is my algebraic equation. Now, how to solve this equation for a given situation is straightforward. We can obtain simplified equations also. Let's say, for example, I want to obtain the generalized equation. So in this particular case, I'm saying the area of the faces and the distance between the neighboring cell centers are equal. So what I can do, I can cancel this out. It's pure interior. I can cancel this out. When I cancel this out, this delta SW is negative. So negative becomes positive. So this becomes my positive phi W. This becomes negative phi P. Similarly, here also delta SS is negative. So this becomes positive phi S and this becomes negative phi P. I can cancel out because the distance between neighboring cell center and the size, the area, this quantity is same in this particular case. If it is a non-uniform grid, then we cannot cancel out, but presently we can cancel out. If we cancel it out, then what we obtain, and if we equate this quantity with that of 0, we can obtain the expression for phi p. And obtaining the expression for phi p is obtaining the solution for phi p is our objective. So phi p for interior control volumes can be simply written as phi w plus phi s plus phi e plus phi n divided by 4. Because this has been cancelled out. See, this is 1 phi p, this is also negative phi p, this is negative phi p, this is negative phi p. So 4 negative phi p's are there. If I take those 4 negative phi p's onto other side of the equation by equating it with 0, then I have 4 phi p is equal to phi e plus phi w plus phi n plus phi s divided by 4. So that becomes my phi p. But that is true for the pure interior control volume or the cell. However, if my cell is, let's say, border cell, I am calling these cells as cell centers as a corner. Let's say and then these 3 cell centers as a border cell centers. If these are the border cell centers, then for border cell center, my delta xw, the distance between west neighboring cell center and cell center under consideration, is not delta x. It is half of that of delta x. So since this is half of delta x, I cannot use the same equation for the border control volumes. So for border control volumes, I have different equations. If it is left, see, if it is left border control volume, this distance is delta x by half. So delta xw is delta x by half. So here, this is delta x by half. So I cannot cancel it out. In that case, 2 will go to the numerator and then I can cancel out. So I will have 2 phi p's here and 2 phi w's here. So similarly here also, for the south face, we will have 2 phi p's and 2 phi s if I am talking about the bottom border line. But if I take simply left border cell centers, then there will be 2 phi p's and 2 phi w's, and the equation for left border for phi p can be written as 2 phi w plus phi s plus phi plus phi n divided by 5, because there are 5 phi p. Similarly, I can do for the right. For right border, delta xe is half of that of delta x by 2. That is delta x by 2. So it's half, and that is for east face. So that is for this particular term. This is my delta x by 2. So if 2 goes to the numerator, this is 2 pi e minus 2 pi p. So for 2 is associated with east face. So that is reflected in the expression for right faces. So phi w plus phi s plus 2 phi e plus phi n is equal to divided by phi is my phi p. In fact, I have given this simplified equation for your understanding only. We can anyway equate this equation with that of 0. All the geometrical parameters are known to us. Phi e, phi w, phi n, and phi s can be known to us from the initial guess. We can make a certain guess for phi, and then only unknown left in the equation is phi p, and we can determine that phi. And we can scroll through all the points. I can determine phi p for this point, this point, this point. I can scroll through all the points and I can determine all the phi p's. That becomes one iteration of the solution. Then you can come back to this point, again calculate new value of phi p. While calculating the value of phi p, what you require is the information about the information at these cell centers for phi, which is known to us either through boundary. This will be known to us from boundary condition, and this will be known to us from initial guess. So thus I can scroll through. Once I scroll through, I get some new values of all the cell centers. Then I can use those new values for determining next new values for all the points. Again, next. We can keep on doing iteration. So carrying out these iterations is essentially called a simulation. So after every iteration, we get new values of phi p's. And then when the values obtained during a consecutive iteration, if those values are same, we can say that we have arrived at the solution. It's possible to do this manually for less number of cell centers. But if I want to obtain the information at large number of cell centers, we cannot do it manually, and we need to make use of a computer to obtain the solution. And when we make use of a computer, we need to write an algorithm. We need to write a code. We will see how to write the algorithm for obtaining solution to such kind of a problem. So these equations I have given for your understanding only. Similar, I will explain how to obtain the expression for the border control volume also. One of the corner control volume, and the rest of the equations you can understand. For example, if I'm considering the left bottom corner control volume, then my delta xw is half delta x, and my delta ys is half delta y. If this is the case, then this is my half delta x by 2, and this is delta y by 2. In this case, 2 goes to the numerator, so I have 2 phi p's and 2 phi w's. Here also 2 goes to the numerator, I have 2 phi p's and 2 phi w's. So 2 phi p's, 1 phi p here, 3, this is 2, this is 5, and this is again 1, 6 phi p's are there. And we have 2 phi w's and 2 phi s, 1 phi e and 1 phi n. So what I obtained is phi p is equal to 2 phi w plus 2 phi s plus phi e plus phi n divided by 6, because I have 6 phi p's. So these are the simplified equations. Similarly, I can obtain equation for left top, right bottom, and so what I mean to say, you need to find out you can obtain the solution manually also if there are less number of cell centers. Solution, I mean to say, you can do 1 or 2 iterations. It is not possible to go ahead with large number of iterations. For going ahead with large number of iterations, of course, you need to write the algorithm and the code, and you can run that code and obtain the solution. I hope I'm able to communicate with you properly. If there is any doubt, quickly I can take up maybe 1 or 2 questions. If you have any doubt. Anybody? Yogesh, you have something to ask?
No, sir, it's okay.
So then I shall proceed. See, so far what we have done, we have discretized domain, then we have discretized the equation also. But then it is essential to discretize the boundary conditions as well. See, many times it is possible that the boundary conditions are available to you in the form in which my computer does not understand. Let's say, for example, here, this is an insulated boundary. What do you mean by insulated boundary? Insulated boundary means I can say dt by dy is equal to 0. That is gradient of temperature is 0. My computer does not understand this differential equation. Computer never understands differential equation. It understands only algebraic equations. So how to convert this differential equation into algebraic equation and how to represent these boundary conditions? So that is done through discretization of the boundary conditions. So, and let me clarify one thing, and you should remember this for forever, that boundary conditions are required, finally required in terms of temperature only. The boundary conditions are finally required in terms of temperature only. So you must know temperatures at these points, blue points. If you know that derivative is, if you know the derivative, that is not sufficient. You need to know temperature. You need to know, if it is a fluid flow problem, you need to know velocity. Knowing the gradient of velocity is not sufficient. So what we have done here, we are going to understand how to discretize the boundary condition so that we can implement it such that I know the temperature at these boundaries. So the first and simplest boundary condition is this boundary is maintained at some constant temperature. This boundary is maintained at some constant temperature. So I can say at x equal to 0, t is equal to tw. Then I can also say T1 for all j's. This is I is equal to 1. So T1 for all j's is equal to TW. This is my simple boundary condition. This boundary condition is also called Dirichlet boundary condition. The Dirichlet boundary conditions means the variable Now here we have in the solution, we have temperature as a variable. The variable itself is constant on the boundary. Such a boundary condition is called Dirichlet boundary condition. And I can say T1J is equal to TW. The bottom boundary is insulated at y is equal to 0, dt by dy is equal to 0. But this dt by dy, my computer does not understand. So what I can do, I can take the difference between neighboring, difference in temperature between neighboring cell centers and divide it by the distance between two. So I can write down, let's say temperature here minus temperature here divided by the distance between two, let us say delta y by 2, and that is equal to 0. That's a discrete representation. Then from that I can obtain the equation temperature here is equal to temperature here. 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 In a generalized form, I can write it as Ti1, that is temperature at J is equal to 1 for all i's, is equal to temperature for J is equal to 2 for all i's. So this temperature difference divided by distance between two is equal to 0. If I equate, I obtain this equation. So now see, the temperature is represented in terms of the inner cell center. The temperature of the inner cell center will be known to us through initial guess to begin with, or maybe through initial condition. Initial guess, initial conditions, we will assign some value, and that value will be automatically assigned to this if I use such kind of equation. Here my boundary condition is again similar. Only thing is that I have the boundary like this now. It is QW is equal to minus K dt by dx. So dt by dx is equal to QW upon minus K. dt by dx is equal to QW upon minus K. So how do I implement dt by dx now? I can take the difference between this temperature and this temperature divided by distance between two. That becomes dt by dx. And that dt by dx is equal to QW upon minus K. Now this temperature difference can be written as temperature at Imax minus temperature at Imax J minus temperature at Imax1 minus Imax minus 1 J divided by delta x by 2. This distance is delta x by 2. So that, and that is equal to, if I multiply that by K, that should give me QW. So from that equation I can derive this T Imax J is equal to T Imax minus 1 J upon plus QW by K into delta x by 2. So again, do understand that this temperature is a function of inner cell temperature. This temperature is a function of inner cell temperature. Here also, this temperature is a function of inner cell temperature. Same thing when it is with the other boundary conditions. This boundary condition is also called a Nyman boundary condition, wherein the derivative of a variable is constant. Here see, dt by dx is QW by minus K. That is constant. Here, whatever heat is conducted is being convected. Whatever heat is being conducted is being convected. Convection is given by H delta T, that is temperature at the face minus the temperature of the environment. T I max, Ij max minus T infinity into H. That's my flux, convection flux. That is equal to heat conduction. So heat conduction is equal to heat convection. By using this expression, I can find out the temperature at all these. So that's my discrete representation of the boundary condition. So these boundary conditions are how to represent. So boundary condition is known to me. I know the discretized equation. I can write down the algorithm for obtaining the solution. I will now explain you the solution algorithm for steady state heat conduction problem. The first and the most important step in this is you need to enter the inputs in terms of material properties, in this particular problem, we don't need material properties because, yeah, we need material properties. Minus k is required. So whatever the material properties are essential, you need to input those. You need to input the geometric parameters like L1 and L2, the maximum number of control volumes in X and Y directions, and boundary conditions which are essential as the input boundary conditions. I'm not saying the actual boundary condition. Boundary conditions input. I mean to say you need to implement, you need to input the value of H, heat transfer coefficient, and T infinity. So these are my boundary conditions input, and I need to also give ETS. It is epsilon. I will come back to this point. What is epsilon? As I go ahead with the explanation of solution algorithm. The next step is grid generation. Calculate all the geometric parameters of all the control volumes. So these parameters which I talked during grid generation, you need to calculate all these parameters for all the cell centers, all the cells. Do remember, these parameters are required to be determined for all the cells, and our objective is to determine the temperature at all the yellow cell centers. Here I am showing you 5 by 5 control volumes, but this number has to be, you can increase as per the requirement of the problem. It may be 51 by 51, it may be 100 by 100, whatever. It is as per your requirement and the level of accuracy which you require. So in a grid generation, what we do, we calculate all the geometric parameters which consist of X and Y coordinates of cell centers, sizes of the faces, areas of the faces, distances between neighboring cell centers and cell center under consideration, and the volume of all the cell centers, all the cells. Then set the initial guess. Initial guess you have to set. If, for example, let's say I have 4 boundaries subjected to, let's say this is subjected to 100 degrees, this is 200, this is 300, this is 400, I can assign some value to these yellow cell centers, and that is my initial guess. That may be 0, that may be 50, that may be 100, or the best is you can take the average of the four temperatures, or you can decide some possible initial guess. Once you decide the initial guess, you can also give the Dirichlet boundary conditions. I mean the boundary conditions in which the variable is constant. Those boundary conditions you can set here. Other non-Dirichlet boundary conditions which I was talking here, this is non-Dirichlet, this is non-Dirichlet, this is non-Dirichlet. This is in fact Neumann boundary condition, and this is Robin boundary condition. So other non-Dirichlet boundary conditions are required to be set at a different instant. Why? Because these non-Dirichlet, in case of a non-Dirichlet boundary conditions, the temperature on the boundary is a function of temperature of the inner cell center. And this temperature of inner cell center is going to change after every iteration. So we need to change the boundary condition after every iteration. And hence, the non-Dirichlet boundary conditions are required to be set separately. Once we set all the boundary conditions and once we give the initial conditions, after that, what has happened? Now we know the temperatures at all the cell centers, including blue and yellow. The yellow temperature at the yellow cell centers is known to us from initial guess, and temperatures at boundary conditions is known to us from boundary conditions. What we do now, we define another variable, that is phi old ij. My regular variable is phi ij. Let's say set another variable, that is phi old ij. It's phi old ij, and we assign all phi ij's to that phi old ij's. So what we do, we are making all the values which are available with us, we are making those values old. So phi old ij is equal to phi ij for all control values. Then for each interior and border control volume, we calculate phi ij, which is new. We can scroll through all the ij's and find out the new values of phi ij. Once we find out all the values of phi ij, what we can do, we can find out the RMS value of phi. What is RMS value? It's root mean square value of phi, to understand whether our solution has converged or not. So how do we find out that? It's a square root of phi ij minus phi old ij whole square. It is done, it is summed up over ij divided by I max minus 2 into j max minus 2. What is I max minus 2 into j max 2 minus 2? This represents the number of cell centers at which we are trying to find out the solution. And we are finding out the solution for yellow cell centers. So I max is, for example, here it is, for example, in this case, it is I max is 7. So 7 max minus 2. That's this goes and this goes. We are finding out for 5 along x direction and 5 along y direction. So I max minus 2, j max minus 2, these are the total number of cell centers at which the solution is being found. So if this value is less than epsilon, which we defined at the beginning, I said EPS. If this value is less than, RMS value is less than epsilon, my solution is converge. Else, go to step number 5, set the non-Dirichlet boundary condition. These boundary conditions are to be updated, and again go through these points. Go back, again go through this point. Thus we iterate many times. And if epsilon is, if RMS phi is less than epsilon, I say that I have reached to solution, and then I can print the values of x, y, and phi. I know the values of x is x coordinates, y are y coordinates, and phi is the temperature. I can find out, print that result, and then I can look at the result and plot it. What I'm doing here now, I'm going to share with you the results obtained for a simple problem, the plate which is subjected to constant temperatures on the boundary. Let's say this is TB1, this is TB2, this is TB3, this is TB4. We have worked with a problem. We have the governing equation as del 2t by del x square plus del 2t by del y square. These are the boundary conditions. At x equal to 0, T1j is equal to TB1. We'll be considering this TB1 as 100. TB2 at y is equal to 0. Ti1 is equal to TB2. This is, we'll be considering as 200. Similarly, other temperatures 300 and 400 are given. This is my algebraic equation, that is the approximate algebraic equation. If I set this equal to 0, I can find out, if I know the from initial guess the temperature of east, west, north, and south places, I can find out Tp. So I can formulate the equation by equating it with equal to 0. If I formulate that equation and if I write the equation for each and every cell center, then I can write as many equations as unknowns as the cell centers are there. So for example, I can write 25 equations for 25 equations for 25 cell centers. I am sharing with you here a solution for 1, 2, 3, 4, 5, 6, 7, 8, and 9. That is a small 3 by 3 matrix. I am 3 by 3. This thing I am considering, that is 9 cell centers I am considering. For each cell center, if I write down these equations, this equation, and then if I write those equations in the matrix form, what I obtain is a pentagonal matrix. So this is a matrix of a coefficient, this is matrix of a variable, and this is matrix of a boundary condition I can write down. And this matrix then can be solved either using Gauss-Seidel method or maybe Gauss-Jordan method, or so on and so forth. What I am doing here, I am giving you the solution, how to represent the solution. So once you are once your algebraic equation is ready, you can put it in the form of a matrix, and you can solve this matrix to obtain the solution for these temperatures, inner temperatures. Right? The boundary temperatures are known to us from boundary conditions. So once I obtain the steady state solution to such kind of a problem, how does solution look like, and how do we plot this solution? We are using a software called TechPlot to carry out the plotting, because my Excel does not provide me the facility to plot the contours. Now, how if I obtain the solution for such kind of a problem, the solution will be available in the form of numbers, but those numbers, from those large numbers, we cannot understand the solution. But if we plot it, then the solution can be understood. So here TB1, TB2, TB3, TB4 are given, and for that how the solution looks like. The the validity to understand this correctness of the solution is to look at whether the central temperature is average of all the 4 temperatures. So here you can see the temperature line in representing 250 degrees Celsius is passing through the center. You can see the 200 degrees Celsius line is only hitting the boundary which is at 200 degrees Celsius. Even 180 degrees Celsius line is going away from this 200 degrees Celsius line. Here also you can. So these kinds of contours, if we are able to plot, these are called steady state temperature line contours. This is one way of representing your result. You can represent result in terms of the flooded contours also. So steady state temperature flooded contours. The contours are flooded. Each of the band of color represents certain temperature. So this is the another way of representing the solution. So essentially, I am sharing with you the solution which is obtained for a simple boundary conditions 100, 200, 300, and 400 degrees Celsius, which we have obtained. This solution we have obtained. We can also determine. I will take 2-3 minutes additionally, maybe beyond 1:30 I will go. Now, additionally, we can also find out the heat transfer across certain face of the plate, which may be of engineering importance. So let's say now this is the data which I have represented for the bottom boundary. The bottom boundary is at 200 degrees Celsius, and I am writing here the temperatures at the inner cell centers, just above the bottom boundary. So these temperatures. So if I take the difference between these two temperatures, these are the steady state temperatures, right? If I take the temperature difference between these two and divide it by the distance between two, what I obtain is the temperature gradient. So this temperature gradient, this temperature gradient is multiplied by minus K. What I obtain is the heat flux across this much part of the control volume. And if I multiply it by this much of area, I get the total heat transfer across this small control volume. If I consider temperature gradient here, I can find out the heat transfer across this. If I consider temperature gradient here, I can find out the temperature heat transfer across this phase. If I consider temperature gradient here, I can find out the temperature heat transfer across this phase. And if I add all those heat transfers, I will obtain the total heat transfer occurring across the bottom phase. This can be done. This is the engineering analysis which we can do. We can essentially calculate the heat flux, local heat flux, and we can also calculate total rate of heat transfer from the bottom. And maybe we can do it for the top also. For every phase we can do, for every side. So Qi1 is equal to minus K Ti minus 2 minus Ti minus 1 upon delta Y by 2. This is temperature gradient multiplied by minus K. That's the flux quantity. If I want to obtain the total heat transfer, then Qi1 is equal to integral 0 to L Qi1 dx. In the numerical form, I can write it as, in the discrete form, I can write it as summation over I is equal to 2 to I max minus 1 Qi1 into delta x. This dx is delta x. I can do this summation. So that gives me total heat transfer. I have just plotted here for your understanding the heat flux across the bottom. You can see this red line indicates, the red symbol indicates the heat flux across the bottom line. You can see If I look at the temperature contours here, in this region, the heat transfer will be in the positive y direction, sorry, negative y direction. So here it is 200 and here, sorry, positive y. So from high temperature to low temperature. On the contrary, here, beyond this particular point, the heat will be transferred from the negative y direction. So you can see the temperature, here my heat transfer, heat flux is positive, and beyond certain point it goes into the negative. It goes into the negative. So that is the indication that the methodology which I have adopted, finite volume methodology which I have adopted, is working well. Through all these representation, I can understand. Try to understand. Our objective here is not to understand the heat transfer process as such. Our objective is to understand the finite volume methodology. We have obtained the results for the other kinds of boundary conditions also. For example, the TB1 is, the left boundary is at 100 degrees Celsius, bottom is insulated. See, the moment your bottom is insulated, the temperature contours are hitting in the direction normal to the wall. The normal direction means there is no temperature gradient, and hence there is no heat transfer. The right boundary is maintained at a constant heat flux. Some constant heat flux is given. See, all the lines which are hitting the right boundary are parallelly hitting to the right boundary. All the lines are hitting parallelly to the right boundary. That means my heat flux is constant here. So essentially what I can ensure through this is that my finite volume methodology which I have studied so far is working well. Here these are the flooded contours. Here again I can do the same thing. I can calculate the local heat flux and the total heat transfer for the given situation. So thus we come to the end of the steady state heat conduction problem. Because of the paucity of the time, it is really not possible to go ahead with the fluid flow problem also. We can again assume the similar kind of, as I said at the beginning, we can consider a simple flow, incompressible inviscid flow. We can, for incompressible inviscid flow, we have a similar kind of equation. We can solve similar kind of equation for the simple problems like flow or a square cylinder, and we can do the domain discretization, and we can obtain the solution to see the streamlines. See, if the flow is inviscid and incompressible, the streamlines are completely attached to the body. This is a simple example of a flow across a square cylinder, but the flow is inviscid and incompressible. If the flow is inviscid and incompressible, there is no vorticity generation, and the flow is completely attached to the body. Similar kind of equations can also be solved for. Similar kind of equations can also be solved for the backward facing step problem. We can discretize in the same fashion. The same equation del 2 psi by del x square plus del 2 psi by del y square can be solved, and the solution can be obtained for the streamlines. Psi represents a streamline, and again you can see there is no vortex formation. In real situation there should be the vortex formation, but since my flow is, since there is no convection present, only diffusion is present, there is no vortex formation in the flow. So that's something about the steady state or pure diffusion problems. If you have any kind of questions, you can go ahead. We'll take one or two questions in. There is a question, please explain how to code the algorithm. I mean, you must be acquainted with some or the coding language, and then each and every step you can, I mean, in the algorithm, each and every this thing is given to you. The expression is given to you. You need to simply write the appropriate syntax for each and every expression and implement the code. Write the code and implement it. Yeah, what is EPS? There is a question. What is EPS? EPS is nothing but it's a small value which we use for, small value of a variable which we use for deciding the convergence of the flow. That was explained in the slide also. EPS is nothing but a very small value. I mean, we define it ourselves to it represents essentially the convergence criteria. EPS is nothing but it's a convergence criteria. This convergence criteria is used. This convergence criteria we set, and if it is less than or equal to RMS of 5, then we say that our solution is converged. So it is essentially the representation between two consecutive results. I hope I have answered to the question which has been raised by Mr. Robo. How to choose EPS? I mean, it depends on the desired level of accuracy. If you want high level of accuracy, its value should be very low. Maybe you can say for a current problem, we can say it as 0.00001. There are other questions like kindly share suggestion, kindly share the slides to us. I will be sharing all the slides. Please explain the way to code. I mean, once I cannot take you through the actual coding process, but I can explain you the algorithm. The algorithm has to be converted in terms of code by yourself. I mean, maybe I will share with you some of the codes which are available with me, written in Scilab. I can share those codes with you, but then you will have to write your code. I mean, if you want to understand computational fluid dynamics in its entirety, you must put on your hands onto code. You must do yourself the coding. The algorithm can be shared with you. I will share some codes also with you, which are available with me. I will send it through email. Is there any question? If there is any question, we will take it up. Verbally, you can ask some question if you have. There is a question, any book which you describe to code? I mean, the codes are available in Professor Atul Sharma's book itself. You can look at those codes. C codes and Scilab codes are available. Is there any doubt, any question? It seems there are no questions, so maybe I will stop for now. And
Sir,
yes.
Sir, for that analyzing the contour plots, so do we have any other books where which will explain how to analyze those contour plots and all?
The contour plots are to be analyzed with your understanding only, because you know physically you know the problem, so you need to correlate or make the relevance between the physics of the problem and the results which you have obtained. I mean, you can see when we will be going through further problems, we will be trying to look at how to analyze also. But as such, you don't get the analysis of the contours in a particular book, because the analysis of a particular problem varies. I mean, the analysis varies from problem to problem.
Okay, problem dependent, no, sir. It actually depends.
And the analysis is also depends on how do you look at the problem. I mean, that there your insight, your own insight into the problem is very important. We can analyze it in a simple way. I mean, now here I have analyzed by simply showing you the temperature contours, but we can derive from that temperature contours, we can derive the temperature information along a particular section and look at that variation. How does it vary? And from that, if we are able to develop some physical understanding, that's nothing but the analysis we call it.
What is the actual significance of plotting the contours, sir? It will tell you
from the contours we can qualitatively understand the physical behavior of the process. Like here we understand the physical behavior of the process, heat transfer process. When I say these contours are there, from this I can understand how my heat is flowing from one location to another location.
okay, physics of the
From the contours essentially we understand the physics.
Okay, yes, sir. Thank you, sir.
Is there any other question? Yeah, kindly say, can you explain the problem solving with a non-uniform grid? See, let us go ahead with the uniform grid first. I mean, within a span of 5 days, I mean, our major focus is will be on the uniform grid only, because our program is for the beginners only. The non-uniform grid, of course, we can go ahead, but for that we need to have a separate time. Fine, then if there are no questions, we will stop here, and we will meet again at 12 o'clock for understanding how to resolve the unsteady state problems. Thank you very much.
Thank you, sir.